Hello, myself Dr. Anuj Purwar. Today I am taking lecture on theory and design of sedimentation part 1. Sedimentation is a physical water treatment process using gravity to remove suspended solid. Solid particles entrained by the turbulence of removing water may be removed naturally by sedimentation in the still water. Settling basins are constructed for the purpose of removing entrained solid by sedimentation. Clarifiers tanks are built with mechanical means for continuous removal of solids being deposited by the sedimentation. Sedimentation process has been used to remove grit in grit chamber, particulate matter in primary settling basin, particulate matter in secondary settling basin, destabilized floc in clarifaculator, biological floc in activated sludge, and solid concentration in the secondary settling tank. Sedimentation is classified into two categories: plain sedimentation and sedimentation with coagulation. Plain sedimentation impurities are separated from the suspended fluid by gravitational force and natural aggregation. Sedimentation with coagulation. Addition of chemical substances known as coagulants increase the aggregation. Finely divided suspended as well as colloidal matter are made to settle here. Depending on the concentration of suspended matter and the characteristics of particles, sedimentation process can be classified in four categories. Here the picture for the types of sedimentation for the four categories. First one is the discrete settling, second one is the flocculate settling, third one is the zone settling, and fourth one is the compression settling. We will discuss in detail in coming slide. Settling of discrete particles. In this type of settling, particles have little or no tendency to flocculate in a dilution suspension. Such particles are known as discrete particles. They settle as individual entities and there is no significant interaction with neighboring particles. The particles keep their size and shape during discrete settling with an independent velocity. In general, if the concentration of the solution is lower than 500 mg per liter of total suspended solid, sedimentation will be considered discrete settling. Settlement of flocculent particles. In this type of settling, flocculent particles in a dilute suspension agglomerate, which causes increase in size, shape, and density. Flocculent settling refers to the sedimentation of particles in a rather dilute suspension with concentration of solid usually less than 1000 mg per liter. The removal of organic suspended solids from raw or untreated sewage in primary settling tanks, settling of chemical flocks in settling tanks, and of bioflocks in the upper portion of secondary settling tanks are the example of the flocculent settling. Zone settling. As the concentration of particles in a suspension is increased, a point is reached where particles are so close together that they no longer settle independently of one another. There is also a net upward flow of liquid displaced by the settling particles. This results in a reduced velocity of particles settling and the effect is known as hinder settling. This is known as zone settling because it is easy to make a distinction between several different zones which separated by concentration discontinuities. Compression settling. The settling particles can contact each other and arise when approaching the floor of the sedimentation tanks at very high particle concentration, so that further settling will only occur in adjust metrics at the sedimentation rate decreasing. In compression zone, the settled solids are compressed by gravity. As the settled solids are compressed under the weight of overlying solids and water is squeezed out while the space gets smaller. So here the picture showing the time versus the depth versus time. So as per time increases, there is a different and there is a different depth of a settling zone. So there is a first we see the water clarified area, then discrete settling area, then flocculent settling. In this is all shown in this beaker where water is retained, and then zone settling, and finally there is a compression settling. Theory and design of sedimentation. If a particle falls freely in a still fluid, accelerate downward due to gravity until the frictional resistance or drag of the fluid equals the driving force. After attaining equilibrium, the particle begin to settle at a uniform velocity, which is known as settling or terminal velocity of the particle. The settling of the particle in the suspension is influenced by the size, shape, and specific gravity of the particle, specific gravity and viscosity of the water, and physical environment of the particle. Here the picture of the free body diagram of a discrete particle which is going to settle in the settling basin. The forces are due to the gravity and the buoyancy force due to the fluid, and the final friction drag force. The downward acceleration of the particle can be obtained from Newton's second law. This is m dv upon dt is equal to Fw minus Fb minus Fd. Here v is the settling velocity of the particle and m its mass. After equilibrium, dv by dt becomes 0. Then Fw minus Fb is equal to Fd. The force acting on the particle due to gravity is given by the relation Fw is equal to rho capital V G. Rho here the density of the particle, capital V the volume of the particle, and G acceleration due to the gravity. The buoyant force Fb is equal to rho W capital V into G. Here rho W is equal to density of the water. The drag force Fd of the water is a function of the dynamic viscosity nu, the density of the water, the settling velocity, and the characteristics diameter d of the particle. The drag force is given by capital Fd is equal to 1 by 2 capital Nd rho W capital A and V square. Here n capital N d is equal to Newton's drag coefficient. Capital A is equal to projected area of the particle at right angle to its motion. Putting values here for the Fw, Fb and Fd. So we get the capital Vg into in bracket rho minus rho W is equal to 1 by 2 capital Nd rho W capital A into V square. Rearranging the terms to obtain a relationship for the settling velocity, then V is equal to under root in bracket 2g divided by Nd multiply in bracket gs minus 1 into capital V divided by the A. Here gs is equal to specific gravity of the particle. Suppose particle's shape is a spherical, then diameter suppose is d. Then in that case ratio of capital V divided by A is equal to pi d cube divided by 6. into 4 divided by the pi d square. So it is here the value is equal to 2 by 3 d. So now v is equal to 4 by 3 into g by nd into gs minus 1 into d. Newton's drag coefficient nd is a function of the Reynolds number Re and the shape of the particle. For Re less than 1, laminar flow condition prevails. Then the relation Nd and Re can be approximated by Nd is equal to 24 divided by the Re. So put the value of Nd here again in the previous equation. Then V is equal to under root G by 18 into Vd divided by the nu into Gs minus 1 into d. Above equation is the Stokes law and the V is in centimeter per second, D in centimeter and nu is nu is equal to centimeter square by second. At high Reynolds number, Nd is approximately constant for turbulence flow. This value is around 0.4 and so put the value Nd is equal to 0.4 in previous equation. So we will get V is equal to 1.82 into under root G into in bracket Gs minus 1 into D. Above equation is known as the Newton's law. The equation applies if the particle's diameter is greater than 1 millimeter. For Reynolds number between 1 and 1000, a transitional flow exists. The relationship between Nd and Re is approximated by the relation given by the Cam and Hazen as Nd is equal to 24 divided by Re plus 3 divided by the root Re plus 0.34 and then V is equal to 2.32 into in bracket rho minus rho w into d की power 1.6 into rho w की power minus 0.4 into nu की power minus 0.6 and whole की power 0.714 where nu is equal to dynamic viscosity of the liquid. Transition flow formula are used for particles of size ranging from 0.1 to 1 mm. Now here is the example. Calculate the settling velocity of water of a spherical discrete particles of 0.05 mm diameter and specific gravity 2.5. The kinematic viscosity is 1.02 into 10 power minus 6 meter square per second at 90 degree centigrade temperature. So here we have to check if the equation used for calculating settling velocity is valid for that case. So from the equation V is equal to G d square divided by 18 nu into Gs minus 1. Putting the values here, we get the V is equal to 0.002 meter per second. So above equation is valid for the laminar flow condition when Reynolds number is less than 1. Hence we should check whether Reynolds number is less than 1 for the given condition. So R is equal to V d square divided by the nu. Keep the all values here. So value comes is equal to 49 into 10 power minus 7. This is less than 1. So the flow is laminar and equation is the applicable. Types of sedimentation tank. Based on methods of operation, there are two types: fill and draw type tank, continuous flow type tank. Based on shape, circular tank, rectangular tank and Hooper bottom tank. Based on the location, primary tank and the secondary sedimentation tank. Fill and draw type sedimentation tank. In case of fill and draw type sedimentation tank, water from inlet is stored for some time. The time may be 24 hours. In that time, the suspended particles are settled at the bottom of the tank. After 24 hours, the water is discharged through the outlet. Settled particles are removed. This removal action requires 6 to 4 hours. So one complete action of sedimentation requires 30 to 40 hours in case of fill and draw type sedimentation tank. Continuous flow type sedimentation tank. In this case, water is not allowed to rest. Flow always takes place but with a very small velocity. During this flow, suspended particles are settled at the bottom of the tank. The flow may be either in horizontal direction or maybe the vertical direction. Now the horizontal flow type sedimentation tank. These tanks generally in rectangular shape. They have more length, about twice its width, because they need to flow more distance to settle all the suspended particles. The maximum permissible velocity in this case is the 0.3 meter per second. Vertical flow type sedimentation tank. The vertical flow type sedimentation tanks are generally in circular shape and flow takes place in the vertical direction. Hopper bottom is provided at the bottom of the tank to dispose the collected sludge. Circular tank. Circular sedimentation tanks are preferred for continuous vertical flow type sedimentation tanks. In this case, influent is sent through central pipe of the tank and radial flow take place. Mechanical sludge scrapers are provided to collect the sludge and collected sludge is carried through the sludge pipe provided at the bottom. Circular tanks are uneconomical as compared to rectangular tank, but they have high clarification efficiency. So here's the picture of the radical flow circular tank. Inlet pipe and outlet pipe and the sludge outlet pipe as discussed earlier. Rectangular tank. Rectangular sedimentation tanks are mostly preferred sedimentation tanks and are used widely. The flow takes place in horizontal direction, that is lengthwise in rectangular tanks. Sometimes baffle valves are provided for rectangular tanks to prevent short circuiting. Maintenance costs are low in case of rectangular sedimentation tanks. These are also suitable for large capacity plant. So here is a picture of the rectangular sedimentation tanks with the baffle valves. Hopper bottom tank. In case of hopper bottom tank, a deflector box is located at the top which deflects the influent coming from central pipe to downward. Sludge is collected at the bottom and it is disposed through the sludge pump. So here is a picture of the hopper bottom settling tank. Here are the different channels, inlet pipe, then deflector box as discussed, sludge outlet pipe is available, and then in bottom there is the sludge collection. Primary sedimentation tank. Primary sedimentation tank is a normal sedimentation tank in which water is stored at rest for some time and sludge collected at bottom and oily matter collected at top are removed. After primary sedimentation process, the wastewater is discharged into aerobic filter where activated sludge process take place. Secondary sedimentation tank. After activated sludge process, the wastewater enters secondary sedimentation tank in which suspended particles contains microbes are removed and are reflected towards aerobic filter to maintain high microbe concentration in aerobic filter. Detention time. This is the theoretical time and the water is detained in a settling basin. It is evaluated as the volume of the tank divided by the rate of flow and it is denoted as the dt. This is equal to the V divided by the Q. Thus it is evident it is that time which would be required by the flow of water to fill the tank if there were no outflows. So detention time T for a rectangular tank is equal to V upon Q is equal to B L H upon Q. Detention time for a circular tank is equal to D square into 0.11 D plus 0.78 H divided by the Q. Here D is equal to diameter of the tank, H is equal to vertical depth at wall or side water depth, and B and L is equal to width and length of the rectangular tank respectively. The formula for a circular tank is based on the fact that the volume of the shape of the circular tank used for sedimentation, which is having a cone shaped bottom with slope 1:1, and its volume is d square into 0.11 d plus 0.78 d h. The detention time usually ranges from between 4 to 8 hours for plain sedimentation and 2 to 4 hours when coagulants are used. This is all about the part 1 of the sedimentation process. In next lecture we will discuss more on the that sedimentation process. Thank you.